Today's speaker is Tomás Aquino. He's a permanent researcher at the Institute for Environmental Assessment and Water Research in Barcelona, which is a part of the Spanish Research Council, National Research Council. Tomás got his undergraduate and master's degrees in physics at the University of Lisbon and his PhD from the University of Notre Dame in the US, if that's correctly pronounced.
Amazingly.
He has had the postdoctoral stays in Barcelona and also at the University of Rennes. And in his research, he uses both analytical and computational methods to develop models of transport, mixing, and reaction for surface and subsurface hydrological systems. And in particular, he does this using stochastic descriptions to capture heterogeneity across scales. The title of his talk, as you can see, is Mixing, Delay, and Restart, Fluid-Solid Reaction Efficiency in Incompletely Mixed Porous Media. So the floor is yours, Tomás.
So hello, everybody. First of all, thanks a lot for having me over. Thank you to the organizers. I'm really happy to give this talk today. I hope everybody can see my slides fine and hear me fine. If you have any problems, please tell me. So let's jump right in. So as Gauto was telling you, my talk today is about the concepts of mixing, delay, and restart, and their relationship to fluid-solid reaction rates in incompletely mixed porous medium. Right, so as you all know, providing clean water and sanitation for everybody is a significant challenge worldwide. In fact, it's significant enough to merit its own United Nations goal. What perhaps fewer people are aware of is that a very large percentage of proposed remediation projects for contaminated soils and groundwater actually failed to meet their proposed goals. So I have the numbers from a US National Research Council report from a decade ago, from 2013, and they reported a staggering 90% of failures to meet the proposed goals. So to me, as a theoretician working in this field, this really highlights the need for better models of transport and reaction in the critical zone. So the critical zone is being defined as the near surface region of the Earth, going from the bottom reaches of groundwater up to the lower portions of the atmosphere, where you have all these coupled biogeochemical processes that drive a variety of phenomena. No? So what I'm arguing is that we need good models of reactive transport in this region, not only for effective design or of effective remediation procedures, but also to model and quantify things like nutrient cycles and any number of biogeochemical processes. So I'm particularly interested in subsurface phenomena, so groundwater. And one challenge that we face in this context is that natural media tend to be highly heterogeneous across scales, which leads to a variety of challenges. No? So in particular, what we find is that reaction rates that we measure in these heterogeneous systems at larger scales are often not what we expect from laboratory measurements, okay? And so the basic reason for this has to do with incomplete mixing. So what do I mean by that? You can think, for example, of a reaction between some dissolved solute reactant that is moving in the fluid phase in your porous medium, let's say your aquifer, okay? And this fluid phase reactant can react with some solid phase component that lives here at the fluid-solid interface in the solid part of your porous medium, right? So especially if your reaction is chemically fast, so locally fast, you can have significant depletion around these reactive regions that diffusion is not sufficiently fast to homogenize over, right? And so this leads to decreased reaction rates. And this kind of idea is at the core of this thing called the scale dependence of reaction rates, which basically just means that the reaction rates that we measure at larger scales, like in the field, are how do you say, consistently significantly smaller than what you measure under well-mixed conditions in the lab. And you see this for things like mineral weathering rates, for precipitation dissolution rates, etc. So here I'm just giving you a simple example from Kang et al. In 2019, where they showed that simply shaking your container where you have your reaction in the lab can lead to quite significant enhancement of reaction rates. Okay. Now, so let's zoom in at the pore scale a little bit. So it has been observed by now multiple times, both in two-dimensional porous media and in three-dimensional porous media, that solid plumes at the pore scale tend to be quite heterogeneous already, right? So we have incomplete mixing right at the pore scale. So of course, this the structure of these plumes, like I was saying, controls reactant fluxes and therefore impacts reaction, right? So the problem again is that these systems are highly heterogeneous. We often don't even know all the details of what these things look like. And it's usually hopeless to resolve all the scales. No? So the question becomes, can we develop large-scale models for, in this case, reaction dynamics that take into account that we have this incomplete mixing at the lower scales, but that don't need to fully resolve all the spatial complexity that is going on across the scales, right? So to summarize this little bit of context that I've been discussing, we face some significant challenges for reactive transport modeling in these systems, and in particular, one of them is subsurface media tend to be highly heterogeneous across scales and tend to be quite difficult to characterize because we don't have direct access to them, right? On top of that, even if we did have complete information, we have all this heterogeneity across scales, and typically a fully resolved model over all these scales is too computationally expensive to be feasible, right? So the questions become, what are the pore scale features that really matter and that control large-scale transport and reaction phenomena? And what do the effective dynamics of these processes actually look like at the larger scales when all this heterogeneity is going on down in the smaller scales? Right, so then the goals, generally speaking, are to develop theoretical frameworks that allow us to obtain predictive models that are based on, let's say, the simplest possible measurable quantities relating to your media. And of course, then to use these methods to design efficient numerical methods that don't need to resolve everything. Right? Now, so in particular for today's talk, I want to talk about this idea of modeling the impact of incomplete mixing and transport limitations on reaction rates through this concept of reaction delay. Then I'll discuss how this reaction delay relates to flow and mixing and how it affects fluid solid reaction rates, in particular under chaotic mixing, which I'll tell you more about, of course. And this part of the talk, which will be the bulk of the talk, is focused on saturated porous media. Now, since I know that at least some people at Pore Lab are interested in this kind of these kinds of phenomena in unsaturated porous media, where you have more than one fluid phase, and since we have started working on that also more recently, I want to discuss some perspectives on applying these ideas to unsaturated flows at the end of the talk. Okay, so before jumping into the bulk of the talk, let me just quickly acknowledge my collaborators. So the people that you see here are people that either have co-authored some of the papers that I will discuss today with me, and or are still working with me at the moment on these topics, right? So these span people here at the IDAEA CSIC, where I am at the moment, but also in geosciences, physics, and chemistry at the University of Rennes in France. Oshri Borman, who's at the Galilee Research Institute in Israel, and also other collaborators at ETH Zurich. Right, so let's get started with the bulk of the talk now. So I want to discuss with you this idea of using reaction delay to model incomplete mixing, right? In particular, so Marco Dens and I here at the IDAEA a few years ago, we developed this method we call the chemical continuous time random walk. So this is a stochastic process that aims to, without resolving all the spatial complexity like I was discussing before, take into account the effect of incomplete mixing on reactions within a stochastic rate. Right? Now, so if you look here at the picture on the left again, the basic idea is quite intuitive. So imagine again that you have some reaction, for example, between some solid fluid phase reactant moving through here in the solid plume, along with the flow and diffusion. And then this component can react with some solid phase reactant that lives at the fluid solid interface. So here at the grain surface, right? Now, so if we have contact between the reactants, the interreaction time, so the time between subsequent reaction events, is dictated by chemistry and leads to what we call a well-mixed reaction time that has an exponential distribution according to work that was done, for example, by Gillespie back in the 70s. So conceptually, again, what we did is quite intuitive, was to add an additional delay time to these interreaction times that takes into account the additional time that it takes for the solid to come together with the other reactants so the reaction can occur, right? So then we developed the theory that allows us, based on this description of the interreaction times, with some distribution of delay times due to the variability in these encounter times, this allows us to predict modified rate laws, so kinetic laws for the chemistry at larger scales, right? And in particular, this kind of approach can predict reaction slowdown associated with a certain kind of delay statistics of the type that I was discussing at the beginning of the talk. So at this point, the question becomes, okay, we have this model that is able to quantify these rate laws, but how do we relate the distributions of these delay times to, say, the structure of our medium and the properties of the flow, so that we can have, a predictive model. So we took some further steps in this direction, me and Tanguy Lebogne at the University of Rennes, where we looked at the delay structure for fluid-solid reactions in porous medium. So in particular, we looked at simple reactions. So we looked at irreversible reactive decay that occurs at a constant rate, but at a constant rate only upon contact with the reactive interface at the fluid-solid interface. Right? So the idea was to relate these delay times of the chemical continuous time random walk to the statistics of the excursions of the solid that starts out in some initial conditions to the interface, right? So that there's some initial time that it takes for the solid to reach the interface. And then if the reaction is not instantaneous, we may need to go back a certain number of times before the reaction can complete. So using the chemical continuous time random walk theory, what we did was relate the interreaction time PDF to, of course, the Dam color number, which measures the relative speed of reaction versus diffusion spreading over a certain spatial scale, okay? And the diffusion time as well, of course, and then the tail of the return times back to the interface here, okay? Then, in addition, if we use the theory to develop an equation for the total surviving mass of reactant, which here is shown in Laplace space. So this is a Laplace transform, lambda is Laplace variable. And again, it depends on the parameters I was just discussing, in particular on the statistics of the return times, but also on the tails of the first passage times from the initial condition to the end. So I'm showing you here some examples of first passage and return time distributions that you might have. And note that they can depend on the Peclet number, as we will see in more detail later in the talk. Now, so we tested this theory for a crystalline porous medium. So in particular, we looked at a body-centered cubic bead pack, or BCC for short. More details on that later in the talk. In any case, so the BCC is simply a regular crystalline arrangement of spherical beads, which represent the grains in our porous medium. And then we have flow and transport through the pore spaces, right? And what we did was we used particle tracking to do, say, direct numerical simulations, so to directly measure numerically the reactive transport according to the rules that I was just mentioning in the previous slide. So where we have decay upon contact with the grains. And then the nice thing about using particle tracking in this context is that we could use essentially the same algorithms to also measure the statistics of first passage and return time excursions to the interface. So then we could compare the direct simulations to the predictions of the theory in terms of these excursion times. So here in this plot, I'm showing you total mass of solute versus time, so surviving mass of solute over time. And here the squares represent the direct numerical simulations, whereas the solid lines, they represent the predictions of the theory based on the excursion times. We can see that you can see that we have a very good match across different dam color numbers, which are shown by the different colors. Now, what I also want to draw your attention to is that this theory captures this type of reaction slowdown effect that we see in this particular system. So the results that you would expect if you consider that the fluid phase, the solid in the fluid phase was completely well mixed, are shown by the circles with dashed lines for different dam color numbers. And if you look at low dam color number, you see that there is essentially no incomplete mixing effect. And this is because when the reaction is slow, diffusion is able to homogenize depletion near the grains resulting from reaction. Whereas as you increase the dam color number, then this depletion effect becomes too strong, too pronounced for diffusion to smooth over quickly enough, and then we can have a significant reaction slowdown, right? So this means that if we had used the well-mixed model, we would not do so well in predicting reaction rates at high dam color numbers. Right, so now we have this theory that works well, gives us a relation between, let's say, reaction rates or evolution of total mass and solid excursions, but we still have to measure these excursions numerically, right? So this is still an advantage because we can measure them for one particular case and then use them to predict reaction rates across dam color numbers, but they must still be measured separately for different Peclet numbers, and they're still quite expensive to compute, right? So in order to better understand these processes and to have a stronger predictive model, what we'd like to have is a model for the impact of geometry on the one side, flow and mixing on the other, on these excursion statistics, so that we can make these quantitative predictions without the need for so much computational simulation, right? So in particular, I want to discuss with you how we can model these excursion times in the context of chaotic mixing caused by chaotic advection. So first of all, what's chaotic advection? Well, simply speaking, chaotic advection occurs when you have exponential divergence of nearby trajectories, right? So what that means is that if you take two initially close by, say, imaginary particles or conceptual particles of solid that get transported by a flow, they diverge very quickly. So they explore the space very efficiently, and this leads to very efficient mixing. That's the fundamental idea. So now, even though the details of the dynamics can be quite complex, so I'm showing you here an example from turbulence, where you have high Reynolds number, unsteady flow, and you often find this kind of pattern. The basic mechanism that usually drives this kind of thing is actually quite intuitive and can be understood by looking at what's called the Baker's map. So the Baker's map is called the Baker's map because it refers to the way that bakers stretch their dough when they're making bread for you, right? So what they do to efficiently mix the dough is they stretch the dough, they fold it over, and they repeat the process, right? So it turns out that this kind of procedure actually exponentially stretches material lines, leads to these kinds of divergence that I was, of nearby points that I was discussing, and quickly leads to efficient mixing. And in fact, you can kind of see this stretching and folding effect taking place here in this turbulent jet, if you look closely, and causing efficient mixing. Now, what's perhaps not very obvious is what this has to do with flow through porous media, right? Because flow through porous media is typically low Reynolds number, it's typically steady, right? So it turns out that in 2 dimensions, for steady flow, you cannot have chaotic advection. But it turns out also that for 3 dimensions you can. And in fact, it has been argued recently that it may actually be the norm rather than the exception, because again, it relies on these sorts of fundamental processes of the Baker's map type that you can argue should occur commonly in porous medium. So what am I talking about? If you look here on the left at a non-chaotic flow through, again, the body-centered cubic feedback through the BCC, what you see is that trajectories essentially just come back to the same point periodically, right? So there is not much mixing caused by the flow because it doesn't really change over large distances, the relative positions of particles. No? On the other hand, if you look at chaotic advection through the same system, which you can have as we'll discuss in more detail soon, it's quite subtle. It doesn't look that different at first glance, but what happens is that your trajectories can braid and bend over and get taken over to different spheres as they move along your medium, right? And so what happens is essentially that as you go through these branching junctions around grains, your material lines get stretched out. And then unlike for the non-chaotic case, this doesn't close back down because there is effectively a rotation between the branching and the merging parts of this process. And this actually leads, you can show, to net exponential stretching, which then leads to chaotic mixing. Right? So this has actually been observed experimentally, actually in this case, not for the regular packing, but rather for a random bead packing, okay? Without getting too much into the details, the main thing that I want to show you is that you get these pinching effects around the saddle point in the velocity field here near grain contacts, actually, near sphere contacts. And then you get stretching around these points. You again get pinching on other points. And overall, this leads to this stretching and folding mechanism, which I think you can see quite clearly here, which actually leads to a Baker's map type phenomenon. And so from there leads to chaotic mixing. Now, so again, there's some argument that this might be the norm rather than exception in 3D, although that's still under debate. But what we ask is, what is the impact of this kind of efficient mixing phenomenon on reaction rates, and in particular on surface reaction rates? So we go back to our BCC, to our body-centered cubic feedback arrangement. And so what I wanted to tell you is that the reason we chose the BCC for this work is not only that it is periodic, so it has some advantages for computation, for the implementation of the simulations, but also that it actually affords us a very convenient way to control what you might call the intensity of chaos in the advection through the system, and so in the mixing. So this intensity of chaos, so to speak, can be measured more formally in terms of what is called the infinite time Lyapunov exponent, which is lambda here shown by colors in this plot, which essentially is the average rate of divergence of nearby trajectories or nearby points in your flow. Right. So what happens is, and that's what this is showing, that the infinite time Lyapunov exponent depends on the orientation angles of your mean flow through the BCC packing with respect to the packing symmetries, right? So for certain mean flow direction choices that align with the packing symmetries, you get these very regular non-chaotic trajectories. But by varying the mean flow direction, then you can vary the strength of chaos and the ensuing mixing. So you can have these very strongly chaotic, very efficiently mixing flows, and these mildly chaotic flows. Okay, so to look at the impact of, again, chaotic mixing on reaction, on fluid-solid reaction dynamics in particular, we looked at what we call reaction efficiency. So reaction efficiency we simply define as the ratio epsilon between the effective reaction rate, so the reaction rate that you actually observe across your full solid plume, and the reaction rate, in this case, the decay rate that you would expect if your fluid phase was fully mixed. Okay. So recall that we have this relationship for the total mass with respect to excursion statistics. So that means that we also have, we can derive a relationship for this reaction efficiency versus these excursion statistics, right? So turns out that this reaction efficiency goes to an asymptotically constant value, which just means that at late times the decay in the system is exponential, but it is exponential according to a rate that is determined not just by the chemistry, but also by the excursion statistics. Right? Before going into the details there, let me say that we can go and measure what this asymptotic reaction efficiency looks like for different, again, intensities of chaos in our BCC as a function of Peclet numbers. So as a function of the ratio between, say, flow rate, average flow rate, and diffusive spreading. Okay. So we see is, as we'd expect, that if we don't have chaotic convection, we don't have much mixing, as I was just arguing, and so there is not much impact on the reaction efficiency with Peclet number. On the other hand, though, if we take chaotic orientations shown here by the different colors, we can have a significant effect on reaction efficiency at large Peclet number. And what's more, this effect does not depend on the intensity of chaos, so the Lyapunov exponent, which we found quite surprising. We'd expect the mixing to be related to this effect, and so to the Lyapunov exponent. So at this point, the question becomes, how do we model this effect so we can predict it and we can understand it? Well, we need a model for what the impact of chaotic mixing is on these excursion statistics, because we know how the asymptotic reaction rate actually relates to these statistics. So in particular, this expression depends on, well, these non-dimensional quantities, of course, the Dam color number as well, that depend on the available reactive surface area, on the mean first passage times to the interface, on the second moment of first passage times, which here is normalized by the mean, so on the variability of first passage times, and also on the variability on the second moment normalized by the mean of return times to the interface. So we can actually do a bit better than that. We can simplify this. It turns out that the variability in return times is actually related to a mean first passage time for a homogeneously distributed solid, initially homogeneously distributed. The reason for that intuitively is that the variability in these return times is related to long trajectories that actually explore the domain. Right? So we can prove this, but I think that's the intuition behind it. Now, so now we need only first passage time information, and we can do the theory in this general case, but to simplify things, I will focus today on what happens if the initial condition itself is homogeneous. So now we just have to worry about the mean first passage times and the second moment of first passage times for a homogeneous initial. And I hope that this will show you more clearly the impact of chaos on these metrics. Right? So let's look at this mean first passage time normalized by its diffusive version. You're going to see the impact of flow on the mean first passage time to the interface in this system. Right? So first look here at the purple squares on the top. So these represent these mean first passage times when you don't have chaotic flow through the BCC, okay, through the body center chemo. So in this case, there is essentially no impact of flow rate of Peclet number on these times, which is as we would expect from the previous discussion. On the other hand, if we look at different chaotic orientations, so different Lyapunov exponents in the BCC, we find again this collapse of the mean first passage time for these different orientations, which is still surprising, but in accordance with what we observed for the reaction efficiency. Now, what was more surprising to us was that we thought that we would be able to explain this phenomenon by looking at what happens when instead of flow, you just apply a Baker's map and then you look at first passage times in this context. But it turns out that this is not the case, right? So if we look at first passage times under repeated application of the Baker's map, what we find is a completely different qualitative behavior with the high Peckley number for the decrease of these first passage times, right? Which to us was a very surprising result, right? So in order to understand this, and again, to come up with a predictive theory, we had the idea of modeling the impact of chaotic mixing by using a restart process, by looking at a first passage process under restart. So first of all, what's a restart process? So again, the idea itself is quite intuitive, right? So for your first passage process, you can ask for the time it takes to complete some kind of search operation. No? So for example, you want to find some targets starting from some point, or maybe you want to find some value in some data structure. You have an algorithm for that. Okay? And now this process that has some first passage time, so some probability of finishing after a certain time, can be subject to restart due to different mechanisms. For example, calling off the search because it's raining too much, or because night came, or whatever. Or maybe because your power went out, or perhaps because you have some strategy that says that if you have spent too long looking for your value, maybe it's better to start again and look somewhere else. Okay. So whatever it is, you can ask the question, how long does this process take to finish if it is subject to restart? And it turns out, perhaps not completely intuitively, that under some conditions, restarting can be beneficial, again, because you might be stuck looking somewhere where the thing that you were looking for was not to begin with, and starting over is just the better call. So what does it have to do with chaotic mixing? So the idea is we say, well, since these particle trajectories, so your imaginary particles of solid that you conceptualize going along your trajectories, they diverge exponentially, they explore the space very efficiently, they forget about where they started out over some characteristic time. So we thought, well, we can model the impact of this mixing as a homogeneous restart of these particle positions, of the solid particle position, over the available pore space. Okay. And this should happen at some characteristic, over some characteristic time associated with some rate, that is the inverse of this characteristic time, that we should somehow relate to the properties of flow and mixing. So for some given restart rate, Kr here, we can determine, just based on general restart theory for restart at the constant rate, what the first passage moments that we need for our reaction efficiency are in terms of this restart rate and the pure diffusive dynamics in the absence of flow, and so in the absence of chaotic mixing and restart in our model. Let me just point out that if you look at fast restart, which means high restart rates, so small and characteristic restart times, these diffusive times actually depend only on the diffusive time itself and the amount of available surface area, which means that the moments actually collapse and they scale in a very simple way with the restart time. So they scale with its square root. Right. So the next question is, how do we model this restart time as a function of Peckley number? And the key to the difference between the BCC simulation, so the dynamics in the porous medium, and the simulations for the Baker's map that I was mentioning before, turns out to be here. So it turns out that it boils down to boundary conditions. It boils down to the presence or absence of no slip boundary condition. So of the fact that in porous media, we typically have zero velocity of the flow at the fluid-solid interface, right? And so the reason for this is that since we are modeling this restart process, this mixing process, in terms of just one single characteristic time, it turns out that the right thing to do is use the slowest mechanism to determine this restart time, and so the restart rate, which is its inverse. Right, so it turns out that the bottleneck, when you have no slip boundaries, is actually the dynamics near the interface. And the reason for this is that flow is small here. So because of the boundary conditions, you develop a shear layer here. Okay. And what happens is, as your particles get restarted or mixed efficiently in the bulk of the flow, at some point they will come close to the grain, and that's when they have the chance to actually react by diffusion. Otherwise, they'll just get restarted before reaching the grain. Now, so if we balance diffusion here in the perpendicular direction, which allows you to either escape or reach the boundary, and escape due to advection on the other side of your sphere, in the case of the BCC, then you can come up with the balance that gives you the typical time over which this happens due to the competition between diffusion and advection. And that gives you a restart time that depends on the typical length of these trajectories, on the typical shear rate or the average shear rate that you get near your reactive interfaces. And then you get a Peckley to the minus 2/3 behavior for restart time divided by diffusion. For slip boundaries, however, it's not like this, right? Because we don't have these small velocities, we don't have this shear layer. So the velocities here near the interface are actually proportional to the mean velocities. And it turns out that just leads you to a restart time that scales like Peckley to the minus 1. So remember that for small restart times, so fast restart, which happens at high Peckley number here, we expect a square root restart time behavior. And at this point, we were quite happy because this agreed with the differences that we saw between the BCC simulations and the Baker's map simulation. But can we get more quantitative with this? Well, turns out that we can, right? So if we look at the full dependency of first passage moments, so mean first passage time and second moment, so variability, if you like, for the BCC across different flow orientations, so across different Lyapunov exponents, again, we see that we have no impact of the Lyapunov exponent. And our theory, which is shown here by the solid lines, captures the simulation results shown by the symbols remarkably well. Again, now we understand, or we have a conceptual picture for why these values don't depend on the Lyapunov exponent. This is because when chaos is present, it ceases being the limiting factor. And so we have shear controlling these dynamics rather than the Lyapunov exponent, which to us was quite a surprising result. So then going back to our original goal, which was to quantify reaction rates, or if you like, reaction efficiency, and the impact of mixing, in particular chaotic mixing on these dynamics, we find that using these theoretical predictions, we reproduce remarkably well reaction rates across different Peckley and Damköhler numbers for the BCC. So that was the bulk of the talk that I wanted to give today relating to saturated media. And I think the key take-home message here is that we have this new approach based on these excursion times, which leads us to a new way to model these excursion times using, in this case, restart theory. And this led us to really quantify and conceptually understand better what turns out to be a remarkably universal behavior under chaotic dynamics. Okay, so before closing today, as I said, I wanted to discuss just a little bit the perspectives that we have for applying these kinds of ideas to unsaturated flows. So if we go back to our critical zone and our subsurface, recall that we have all this heterogeneity to deal with. So what happens is that if you look at a typical soil, we have an additional phase, we have an air phase, not just water, and that actually enhances structural heterogeneity with regards to flow, because we tend to form all these preferential flow paths due to the presence of air clusters, which lead also to the formation of these stagnation regions of low flow velocity. So again, for a certain already complex heterogeneous medium, we actually enhance that heterogeneity by adding another phase. Right? So it turns out that this has quite a significant impact, as you'd expect, on the statistics of velocities So for example, on the velocity PDF, on the probability that you find a certain velocity value across your medium. So recently with the collaborators at ETH, we worked on developing a model for these velocity statistics. And we were able to use this model to look at purely advective transport through this kind of, in this case, two-dimensional unsaturated medium. What happens though is we are interested now in understanding how adding diffusion to this picture and subsequent reaction when you come into contact with solid grains is affected by this variability in velocities. So as we've seen, different flow structures can lead to different mixing properties. So our intuition says that this should have a significant impact on reaction rates. So in fact, this has been observed to some extent for fluid-fluid reactions. So for reactions between different reactive components in fluid phase, right? So Joaquin Jimenez and others have run two-dimensional experiments for fixed phase distributions, where they saw that when you go from saturated to unsaturated conditions, this enhancement of heterogeneity that leads to these complex patterns also leads to enhanced deformation of the mixing fronts, which in turn leads to enhanced reactions. This has been observed, let's say, semi-experimentally, so based on conservative, on mixing estimates from conservative experiments for an instantaneous reaction, both for reversible and irreversible bimolecular fluid-fluid reactions. And what is seen that if you compare the amount of product formed in these reactions for saturated conditions here, and unsaturated conditions here and in this direction, we find enhanced formation of product and so enhanced reaction rates. However, as far as I'm aware, much less is known about what happens for fluid-solid reactions, but we expect that a similar effect should be present. So at the moment, I've been working on this particle tracking implementation to run simulations of these dynamics, together also with collaborators at the University of Rennes again. And the idea is we use open foam simulations for the flow, and then we couple these with a homebrew particle tracking that uses also open foam features in order to run reactive particle tracking simulations. You can see a preliminary example here in the video. And the idea is that if we have these particle tracking simulations, again, we will be able to measure not only directly the reactive transport dynamics, but also these excursion statistics that we believe can give us important clues on how to model this. So again, this is very much work in progress, but I thought I'd share this with you because we're quite excited about this direction. So with that, I'm going to conclude. I'm going to make a quick overview of the talk first. So I've discussed with you how we can model incomplete mixing in terms of reaction delay, which is related to transport limitations in heterogeneous porous media. I've shown you how, in particular for fluid-solid reaction rates, we are able to relate these delay statistics to the statistics of excursions of solute to the reactive interface. And then I've told you how we can use, how we can model these excursion statistics to understand the impact of mixing on reaction efficiency. And in particular, I've discussed a model for this type of effect under chaotic flow. So this led us to understand that the details for chaotic flow are actually independent of the details of chaos, surprisingly, and actually are controlled by interface shear. So again, current and future work in these topics that we are carrying out or plan to carry out relate to first reaction rates. What happens to reaction rate when we have unsaturated flow conditions, as I was just discussing. And another avenue would be to look at more complex chemistry, so nonlinear reaction networks, for example, and also more ambitiously to look at the impact of the coupling between flow, medium structure, and reaction dynamics that you can get, for example, if you have precipitation dissolution reactions. So with that, I conclude. Thank you very much for your attention, and I have time for questions, I hope.